welcome to the stream. Hope you're having a good Sunday. And we're about ready to finish up Chapter 6 of Essentials of Compilation. I hope this has been as interesting for you as it has been for me. It's been challenging. We've tackled a lot of new concepts. And we're just about done with register allocation. So our last steps are really about adjusting the allocation algorithm so that we spill heap allocated variables to the root stack rather than into the call stack or into a register. And we were very close to getting to that point last time. We were looking at the interference graph, so determining what locations are in conflict with one another. This is part of the graph coloring, or at least it's the predecessor for the graph coloring. So you kind of, we're basically doing Sudoku with the registers and the stack. But so we're about to get ready to finish that up, and I believe that once we're done with that, the rest of this should be very straightforward. It looks like the prelude and conclusion, which is the boilerplate that wraps the code that we generate, is going to be very interesting. We will need to make sure that we can get information about how many things were spilled to the heap via the root stack, because we have to initialize that root stack when we enter our function. Enter our program actually. So I think we should get started, and we'll see how far we get today. I hope to finish. When I say finish, also I want to say that I'm talking about the main content of Chapter 6. There are 2 or 3 challenges at the end that are really interesting, but the reason why I say I want to finish today is that there's a Gleam game jam coming in November. It's I think it starts on November 25th. So I would like to consider participating in that. Maybe it won't be, it's 9 days long, I think. Maybe it won't be like a full 9 days of me working on it. But I would like to get to the point where I could produce something, and maybe we can do that on stream. I could add extra streams as necessary to work on that. There's this wonderful framework called Tiramisu. It's basically bindings to 3.js and also to Rapier for physics. So you've got a lot out of the box. And as far as the how you work with it, it looks a lot and feels a lot like Lustre, which I think is just a brilliant concept for doing that sort of thing in a functional programming language. That model view update pulls apart the things that you're concerned with into very digestible pieces. And I suspect that they have some pretty clever update algorithms, because one of the challenges, especially with 3-dimensional rendering, is that your drivers, your whole stack that is supplying your graphics card with things to do is pretty stateful. And that feeling of, in an FP language, you want to be mostly stateless. You want to talk about transformations from one data type or one state of data into another state, but you don't really care about retention. And when you try to build in retention, then things get complicated. So I suspect that they're doing clever things with IDs. If you think about how a lot of front-end frameworks work with things like React or whatever, and they rely on diffing in some cases, but in other cases they're like, well, you have to explicitly set the key on a particular element, so we know when a collection changes whether a key was moved in the order or added or removed, and that kind of that sort of thing is necessary to do when your design is mostly functional looking. Anyway, should be really exciting. I've looked at the library; it's really well documented, and maybe we can go in there and, I don't know, do something fun. We'll try to do some learning experiments, and see if we can be prepared to meet the prompt of the game jam. So that's my plan for November. I realize it's November 2nd today, so we'll start next week with that. And but let's get on to finishing chapter 6. So let me switch over here. All right, so we were in register allocation. Remember last time we finished up some things with propagating types way deep into our phases. There may be long-term consequences for that could get to be a pain, but I felt like it was necessary so that we can be sure that when we get to this phase, we're not guessing at which things are actually heap allocated, right? Okay, so yeah, so we use build interference. Okay, so they're saying the spelling of tuple type variables to the root stack can be handled after graph coloring in choosing how to assign the colors to registers and stack locations. So, so here's an important part that will come up when we do the prelude and conclusion. The output of this pass also changes to record the number of spills to the root stack. So we need to know how many variables are on the root stack, essentially. And I think that we can probably do that fairly straightforwardly by iterating over the graph, the nodes, once they're colored. Okay, so last time, note we printed out, we added to our output the live before sets, so that we could see, you know, does this make sense? Are we retaining the things? And the big thing here that I wanted to find out was, you know, R15, which is where the root stack gets placed, that persists in the live before, so that nothing gets placed there, right? And I think that is the case. There are some variables in here, and these are like initialization variables for our vectors in this particular program. So, yeah, you know, we have had these. This is just in UI.gleam. Let's fix that little warning first, and I'm just gonna make a function in here called unwrap both. And then they've deprecated it, but I want to keep using it here, so we're just going to call it unwrap both, not result.unwrap both. That should resolve those warnings. Oh yeah, and now it's saying we don't need to import. Cool. All right, and I should figure out where this is happening. We were doing that last time, and I think it was in build interference test. Right, we were doing it here. So we can just remove that. And I think that covers what we needed to cover for the interference test. Okay. We're just gonna quiet warnings and remove printout in test. Okay. Okay. So I think that um, we should maybe look into this, see if these fail. Let's run Gleam test again after and I saved. Okay, so somehow this is not in conflict with RAX. Yeah. Here, we don't need those two things. So I'm not incredibly concerned that this is going to cause a problem, but because they say in the book it's already in conflict with the callee save registers. I don't know. Okay. Okay. So now that we have the interference graph, our next phase, our next pass, would be allocate registers. So they're saying okay, so we have this bit in here. Let me hide the shell for a second. It's taking the conflicts and it's doing the graph coloring algorithm, which we basically and there's a library that has this unfold like function, but we go with the accumulator, and then right. So what we're trying to output is a list of nodes. And then we're adding this onto this list at the end. So if the generator, which in our case is color graph step, so like take one step in the graph coloring algorithm, we pick a vertex, and right, and so then it's like picking a color based on the saturation set, and then right, so we give it an assignment, and this color is actually a location or an int, right? So we just use integers, and then at the end, right? So we update the adjacent nodes that are unassigned, I believe. No, we just fill in the saturation. Like even if they're assigned already, it's fine to say, hey, there's a conflict between this particular node and the assignment of the adjacent node, right? So it doesn't actually matter that it might already be assigned. Okay, and then we take the output of this new graph and we return it, and this value is the color of I'm sorry, it's the node and its updated assignment. Okay, so this is just to refresh my memory because it's been a while since we touched this, but and we're gonna have to make some modifications in here. So pick color is just a wrapper around this internal tail recursive loop. Like if the saturation set, this is what we're calling, if the saturation set contains this candidate, then it'll continue looping. Otherwise, it says, hey, that's unassigned, so you can take that as the color. And then the pick vertex algorithm here is about like picking which one to do next. So it's saying, yeah, if you've got, we'll take all the nodes in the graph, and we're going to filter the ones that have an assignment out, so we don't use those. If we if it if the node has not been assigned a register or stack location, then we output like what is the saturation, the size of the saturation set, and then it's sorting by that size. And if the size is the same, then we sort by the location. So we had to define this compare location function. And then it's going to take the max by that first element. So it's sorted. Interestingly, I think that we could probably take the last of the list, but list max will works just fine. So takes the list and returns the maximum on the list. And if there's nothing in there, if there's nothing in the list, you get null, right? Yeah, so we do result map and take the second. So we just want the node ID. This is really just about picking which vertex to color next. Okay, let's look quickly at this extract assignments. So a list of nodes, and what we want is okay, so we're taking this location and what is int.arg? Oh, yeah, so we need to say, we're going to have to make some updates here because this has not been changed. Right, so when we did while loops, we didn't need any changes to the assembly language, but now we need changes to the assembly language, so we're going to have to change this. I'll want to rename this, I think it's just going to be x86 global, and then probably x86 varif is going to be x86 global as well. Okay, so in this extract assignments, we're calling this from that allocate registers function up at the top. It's folding over the list of nodes, and it's taking the assignment and it's turning it into an arg. So an arg is like an argument to an assembly instruction. And here, right, you're doing, if it's -1, we get RIX. So this is like mapping back what we did over here, register to rank. So this is the reverse mapping of that. Plus, if it's greater than 10, then you spill onto the stack, right? So, and this is dereffing off of the base pointer. Interesting, it's off the base pointer, not the stack pointer. Okay. So, I think what we need to do is we need to, that can stay. Final reference is not working. Let's find int dot. Okay, so this is, all right, so this one we had two different assembly languages and they're producing different programs, but I think in our case for this one, we haven't created a new one. And the only difference here would be that variables will get removed. I'm not convinced that we need to maybe we need to so that we can record the number of spills to the root. Let's look back at allocate registers. Also, there's some things here in x86 int. Yeah, so the blocks get stack vars. And I think that we just need to put that in the program. And we also need the number of heap spills. So let's look at allocate registers. Where were we? If we look at what they say in the book here with the diagram, they're saying this is x86 var global all up to this point. And I think that there's a mistake here. At this phase, variables would be removed, right? We still have globals, but variables would be removed. It wouldn't be removed in patch instructions. It would be removed in allocate registers because we're giving... Hi, Chris. Great to see you. Sorry about the delay. Wow. I think this is actually wrong. If you want to be pedantic, which I'm so good at. So I think that what I want to do is rename symbol work. No. Okay. This is the input language. So we're going to replace var dot with, I'm going to call it x86 in, and replace all. Undo that. Undo, please. Okay, x86 in dot. I have to put the dot back on there. Okay. And this will be x86 in. Okay, and then for int, this is just, we're kind of future-proofing here. Int dot. I want to replace that with out, x86 out. Hello? What am I doing? Okay, int dot x86 out. Okay. And then yeah, in this case are we not using that? Interesting. Okay. Or is the problem that I broke it? Oh yeah. In this case, this is I messed that up. This is int.compare. Chris, I don't know if you saw early in the stream, I'm thinking about doing the Gleam game jam, which is pretty cool. So that should be fun. Using tiramisu. Okay, yeah. So here, I'm gonna say Gleam x86 out because I messed it up. We're gonna change that to int. What is my problem today? Okay, replace all. There we go. The Gleam Game Jam starts on November 25th. Let me bring it up real quick. Game Jam. Yeah, here. And they've got this cool little website. There's info and rules. So yeah, November 21st. I'm sorry, I was wrong. Lots of details here. Yeah, and I think that, like, for all the things that Bevy makes powerful. Sometimes it makes things complicated, and was not enough to wrap my brain around. So I'm looking forward to this. I didn't show any of this, but like tiramisu, it's all browser based, so it's 3.js, and they've got Rapier linked in here, I think. And again, they see zero runtime overhead. I'm like, yeah, but JavaScript. Um, what they mean to say is it's none above JavaScript because Gleam compiles directly to JavaScript. And it's got the tiramisu has the whole MVU model, which is it's gonna be fun. And yeah, so you can see sort of here, like you can think of it very discreetly as handle messages in update. The view returns your scene, and the init returns your model and any effects that you want to create. So very, very cool. And honestly, it's amazing how fast they built tiramisu. Right. It's not a wholly new framework. I was kind of curious. Sorry for the digression here. I was kind of curious how they do identifiers, but it looks like, yeah, you just create IDs for your objects. I suppose you could use almost any type, but that's how they do the structural diffing as they go. Is this the same ID? Yeah. Is it changed? That sort of thing. So, should be fun. And we're going to get started trying some things next weekend, I think. So, my goal is to finish chapter 6 today. No pressure. Okay, so we've updated that. So now there's a question in my mind. Do I go ahead and say, let's make a version of this without... because we're going to need some new stuff in the program itself. Or do we just add those things to this program? And then, deal with all of the things that we need to deal with in here. I think I want to deobfuscate these aliases a little bit. This is like, we're only working in assembly here. So what if we, at the risk of messing it up again, what if we change x86 dot into x86 base dot and just remove the alias? I think that's probably a wise thing to do. And then, yeah, I don't feel the need to create a new language, so I'm just going to say x86 global as x86, and then we will do replace out with that and replace in with that. Okay, so now those are unused, and we're just gonna have to fix a bunch of things. That's fine. Yeah, I'll be streaming that game jam prep. So should be really fun. All right, so we need to look over here at what's in a block, and I think that what we do is do block here, body is new instructions. That fixes that. And our program, we need to have some new fields here. So what we'll do is we'll take we'll splat our input here. And we need to say, we need to put some new fields on it. Yeah, I think this is the simplest way forward. Where is our type definition for that? Is it way at the bottom? Block, arg, instruction. Here it is. I'm gonna move this up. It's so annoying. Put all the types first and then write functions. Okay, so we're gonna put what are the things we need? Stacked vars and used call e. Okay, so these are the registers that we use that we need to restore at the end of our prelude or at our conclusion, right? So let's just put it here at the end. Stack vars, we'll say, and that's not that. This is an int, right? Yep. Used call e. Where did we define that? So that's a set of registers. Okay. The other thing that we need to do is record the root stack size. So this is a new thing. Okay, stack vars is 0, used call e is set new, and root stack size is 0. Okay, and this, I'm certain this is going to break a ton of things. Okay, so they say, not there. Here. They say it can be handled after graph coloring. So it looks like we have a bunch of things to fix here, of course. So let's go ahead and fix those. Oh, right. So this is rewriting the block after we've done the graph coloring. So we're going to do and q and say translate location, A assignments, B assignments. The other thing here is that I'm pretty sure there's a bit where we need to handle global variables that we had not yet handled. Can you all hear my cat snoring over there? Okay, so yeah, and that's here. Add missing patterns. So deref, there's really nothing to translate there, right? And I think that I can do, yeah, we can just underscore those. This is a trick I learned the other day. You can treat that as just a pattern. And honestly, these we could combine these into the same clause. That's nice. Why don't we do that? So if we do stuff like this, and honestly, we don't even need to alias at all because we have not transformed the thing at all. We can just say L. Okay. The global variable will be turned into that. I forget what they call it, but it's the addressing mode where your static location is offset by the instruction pointer, or the static location is the offset to the instruction pointer. That weird addressing mode. Okay, so that covers everything as far as the new constructs. So the thing now that I'm concerned about, okay, so we have types here. Maybe what we should do is just see what the output of allocate registers is on our sample program. So if we go down here, yeah, this is all commented out. So we can go uncomment that. And we're going to have to find in here and do the int dot. Let's see. Let's start with x86 var if dot, and we're going to replace all of those with x86. Okay. And then we'll do int dot. Yeah. Okay. And now I think we can get rid of that. I accept that we're going to need to get these imports copied over here. Those can go away. All this comes back. Okay. Okay, so I think that what we should do here is just say block, and then we should say block dot body, right? That'll simplify that. What did this call? Okay, so this is start body, so let's call this start, and this will be start dot body. That'll simplify that a little bit. This is a then dot body. I just want to make sure that we can get these tests still working. And this is else dot body. Because we're going to have some things in here that need to change for sure. Oh, okay, so up here. Okay, so we can say base block body is that, right? This is going to fail. We have a base program. We do not. So we can do, and I think this is going to fail because it's not going to be exactly equal. I have a suspicion. Okay, so select instructions test. Oh, yeah. All right, so we probably need to just do that to resolve that problem. Okay. We definitely got some things that are different. Finding the diff there is going to be very interesting. There's a lot of noise because of all that graph stuff in there. Let's just... That's what we expected. Here's what we got. All right, the other thing that we have in here is we have types, potentially. These tests will probably likely have to be changed because we need to fill in that type information. Here, we can just say this base program. Okay. So this is the live after that we constructed by hand. The thing is, at this point, I feel like these are only integer type variables. I don't think that it makes a difference, but we will have inferred that at this point. So, yeah, 7 months ago, man. Wow. We've been doing this a while. Okay, so what I want to do is do this. We say let types. And then we need to make sure that that's also in this one. So our types are going to be here it needs to be the string to type, right? So let's import UC nope Lang's L2 as L. So V is going to be int t, integer t. All of these are actually going to be integer t, so that's pretty easy. We'll have W, we'll have X, have Y, we have Z, and we have T. Okay. Again, this is not going to pass. You know, we are not. We need to do the same sort of treatment down here. So why don't I just copy paste this stuff? I'm beginning to wonder whether we go back and redo these, especially this one that we have. But it won't be very very difficult. Come on, kitty. All right. So why don't we just paste it down here, and we'll put that in this program. Okay, we're not checking full programming quality there. We're just checking the blocks and what they end up being. So we can say A is an integer, B is an integer, C is an integer, D is an integer. And get rid of the rest. Again, this is not going to make any difference. I just want to make sure that this test doesn't panic or something when we check the types of variables in here to make sure that they spill to the root stack. I want to take a brief detour, and I'm trying to remember the name of the package here. There's one that it's like stream, or let's just say iterator. Is it iterators? I honestly think it was. Let's have a look at this. No. Although this looks like a useful package. Okay, there's from list. No, it was something else. It was like stream. Let's have a look. It's like lazy streams. I don't think this was it. Although this would be a pretty powerful library to know about. Lazy pull based, right? Okay, well you construct a stream which has a pull function, and that returns. Okay, so you could return none, and this returns the next value, which is basically what we built in here. And then you could, All right, well, maybe next time. Good to know. I think it's this GS one. I had seen it before. Okay, trying to get back on track here. I think that, right, so we communicate this type into build interference, right? Right, so here we're saying if it's a vector type, we're going to put a conflict. Okay, so we make sure that the variable that we've got is in the interference graph. And then we add a conflict between the variable and all the call eSave registers. Okay, so that's going to make sure that it does not get put into a register that has to be restored. It's amazing how dense these like 3 paragraphs are. Okay, so the garbage collector needs to access all the pointers in the root set, that is all variables that are tuples. It will be the responsibility of the register allocator to make sure that the root stack is used for spilling tuple typed variables. Okay. If a tuple type variable is live during the call to the collector, it must be spilled to ensure that it is visible to the collector. Okay, so the latter responsibility can be handled during construction of the interference graph by adding interference edges between the call live tuple. Right. Okay. So and the callee save registers, right? Because we are like the calling the garbage collector. That is a subroutine call. Like so, you're expected to follow the ABI, the x86 ABI there, the C ABI, which means you save your own variables and you expect that the callee save registers might be modified. Okay, so it's saying they already interfere with caller save registers. Okay, so that handles point 2. So spilling them to the root stack can be handled after graph coloring. In choosing how to assign the colors to registers and stack locations. So I think what they're saying is this translation should not be static anymore. I think they're saying output of this pass changes to also record the number of spills to the root stack. I think that what they're saying here is we need to look at the types of variables. Okay, what do we do? We're doing extract assignments. Right. Okay, so this bit needs to get modified to take into account I kind of want to go let's go up here. Oops. I kind of want to do echo here and like see what happens. And I don't think that this is, it's not going to do what we need because there's nothing interesting there. But what we'll get is the nodes and how they're colored. So maybe let's go back to our test and let's make I'm going to comment these out. We need to be able to fix them, but we need something with vectors. And we're going to, what comes before this build interference? Do we have some? Yeah, let's just copy this business into our file. So what we'll do in here is we'll do our typical thing that we've done in our previous sessions, where we just take this program. Yeah, here, let's just copy that. And then we're going to do let's just echo the output of that. Except we don't need to echo it because it's going to be echoed. What we want to see is how these things are assigned, right? So, okay. So we can look at the stuff that we've done before. Oh, yeah. The other thing that we can do here is so we'll pass that to allocate registers, and then we're going to go I actually want to do IO print line. Here, we'll extract that. Yeah. Sorry if it feels like I'm flailing. I'm just being a little bit slow today. Okay, so what I want to see is what is the output of the program so we can see what the variables are. And then we'll get, that's interesting that came after this. Okay, so temp 7. Is assigned to 0, which is like RCX, I believe. Not in there. So 0 RCX, temp 7. What is temp 7 in this case? Okay, so we are what I want to see is right, so I want to see alloc2 be assigned to an offset of R15, which is something we haven't done yet, right? And we need to know that this is a vector type variable when we assign the register, just regardless of what color it is. Okay, so yeah, temp 7 got position 0, underscore 8 got position 0. A bunch of these underscore ones got assigned things. The underscore ones are ignores. We only care about like the generated ones, these like temp variables, and the alloc ones. Okay, so vecinit got put in RDX. The interesting thing here is that so alloc2 got put in RCX as well as temp7. Does that make sense? Yeah, I think that they are. Yeah, I think that they are not in conflict. Okay, so maybe what I want to do here is not actually print out the entire the entire list of assignments, but maybe we can look at standard lib, do something with list, and just like splat them out. Okay, so each returns nil. We don't want to do that. We could just do map. And as a node. And we'll just do echo. We'll say n dot need the arrow there. N dot location, n dot assignment, and just return it. And so we kind of have a no op there, but not exactly. Okay, so what we should get, yeah, there's a little bit of noise there. We're getting just the locations. And there's, you know, the thing is there's not many. There's not many here, right? The problem is what I would like to see is I would like to see some of these tuple type variables be assigned to the same locations. So like and I guess they are? No, this is like you take this initial, because this is the 42 in the inner vector, right? That's vecinit 1. That's RDX. And then you move that into the heap. So we can see where's vecinit 1 used. So vecinit 1 is created here, right? So if that's put in RDX, that's fine. It's just an integer. And then you jump to block 5 or 6, which determines do you call collect or not. Okay, we're never going to call collect in this program. But regardless, you jump to block 4, and then vecinit 1 is, here it's moved into 8 bytes beyond the pointer at R11, which makes sense. So so that's fine with vecinit 1. Now vecinit 5, we have to scroll up a bit more. So vecinit 5 is the same as this allocation we made. So so this is like move from a tuple type variable into another tuple type variable. So I would not want to see that be put into a register. So what's interesting here is let's look at note that like this is the allocation of this initial variable. So temp 1 and 2 should have the same location. Whoa. Okay, so that's just, yeah. Okay, so temp 1 and 2 should have the same location. They should be assigned the same variable. And they are. It's 0. So I think what's happening here in this coloring is that we need to look at the types. So I'm gonna have that print out. We're gonna get a lot of mess here. It's fine. I'm gonna have that print out here. What we should see is that when we look at temp 1 and 2, this is not register 0 or stack location 0, but root stack location 0. And then the same for the other, so like vecinit 5 is not, although here's the thing, this is just wrong if that's the case, because vecinit 5 should not be a different root. That's the same as alloc 2. So we have we have some figuring out to do here, because what I want to see is and I think that our assignments here, as far as, well, let's see what temp 6 is. Oh no, temp 6 is yeah, that's fine. What I would want to see is for all of our variables that contain vectors, like pointers to vectors, we can assign them to root stack locations. So maybe here maybe we pass in types, right? So this will be a dict between this is a string to an L dot type, right? And these locations in this list are always going to be vars, right? Because the coloring this will never pick register vertices, right? It's like, hey, you know, if you're not assigned, well, of course, that's the thing, is like the registers start as assigned. So I need to think a little bit more about, did we get the they say they already conflict with caller save registers. I mean, is this not all the registers if you combine these two sets? I wonder. I don't know where that assertion comes from, right? They already interfere with the caller save registers. I wonder if that has to do with the globals and so forth. Oh, interestingly, I think, no, that's in call saved. Okay. So we need to pass input.types as an argument here. And then we need to think about where's extract assignments. Okay. So for each node, I think that what we need to do is do a combination of pattern matching here. So we'll do node location, and we'll also match on it is dictionary get of Well, we're going to have to do if it's a location var, right? Because I think I want to see if we get a like maybe what we say here is we make an assigner. And we'll just use nested cases here. And we'll say assigner. Assume this is a function that takes an integer and returns that. Okay, so what we'll do is if it's a variable, then we do another case of dictionary get of from types v, and okay, so here we just say right, that's going to be our function that we are returning here. If this is a okay, if it's an OK and it's a vector t, right? Vector t, that's what we expect here. Then we need to do not just assignment to arg, but we need root. We'll call it root stack assignment. This is very, if it's anything else, we'll do assignment to arg. I kind of wanted to make that into a simple thing, but this is just going to be x86.arg, and we're going to take, those are always going to be positive numbers, so we'll do this is going to be x86.dref, and we're going to do off of R15, and that's going to be 8 times A. Okay, so this is messy. I would prefer to do it some other way. But what I want to see now is, I'm trying to keep focused because you got multiple layers of problems here. I'm going to remove some of these echoes. Remove that. And then we need to go through here and look at the assignments. And we're going to say we know that there are, we need to know the root stack size, right? So we're going to say root stack size, and we'll put that in here. we're going to go over the assignments. And we're also going to do dictionary values because we don't care about the keys anymore. For this particular calculation, we're going to do a filter map. And we'll say case arg. So this is no longer sufficient. The stack vars, this needs to be RVP, right? And this needs to be dref R15. And we're going to say offset. And this really, we just really need to find the unique values. Okay, so why do I have two case args there? Okay, so we've got that. And this needs to be, so we've got a list. I have too many braces there. Okay, I was like, why is that? Why does that look weird? Okay, so that's going to give us a list of all the offsets off of R15. And we'll do set from list, right? So if two variables are assigned to the same position in the root stack, we know that they're basically should be the same thing. Assuming our allocation strategy is correct. And then I want to do size. So that's our that'll give us our root stack size. Oh, root underscore stack size. That's fine. Okay, so the stack variables, it's a number of stack variables, and that's basically how much do we have to push the stack, right? Or move the stack. Okay. And note that the stack grows down and the root stack grows up. These are all negative, and these are positive. Okay, so what I want to do now is go. Let's just print that out. So I removed the prints, I think, from in here. What are the other things that we're missing? No, we just added that, and we have the types, so we're good there. Yep. Okay, so that is a mess. Maybe what I want to do here is go let P2 is this, and then we can. I want to echo some things out, so like P2 dot root stack size. I don't want to print out the whole program. Although honestly, that's the trailing field on it. Should be easy to see. So it's saying it's only one, which is interesting because I think that's wrong. Let's go ahead and do format program. So this is the program before, and actually we can, yeah, let's just copy that. Save myself some time. Yeah, okay. And I just want to sanity check that the program looks like it makes sense. and I'm not sure that it does. So okay, so here we're saying there's a let's start from the start block, which is the first one. Okay, so it moves 42 into RDX. It moves the free pointer into RCX. It should actually move the free pointer into 0 of R15, right? And then this will get removed. It adds 16 to RCX. Okay, and then it moves this global pointer into RSI, compares them, and jumps to block 5 if less than, right, jumps to block 6. So block 6 is where you call collect. Okay, and the RDI and RSI, the arguments to collect. Okay, otherwise you move 0 into RCX. So the thing that's messed up here is that what are we doing here? We've like obliterated this allocation, basically. This is not going to the right place. It's getting assigned RCX. And it shouldn't be. It should be assigned 0 off of R15. Or 1 off of R15. We don't actually care. Or not 1, but like 8. 8 bytes. The only thing I can think here, and we need to let's look at the types assigned, right? The only thing I can think here is that what we've done. Let's print out the program before we do allocate registers. What we've done is temp.1. Yeah, see, temp.1 is not in the types. We generated that in an intermediate pass. It moves, so just is temp.2 in there. Temp.2 is an integer. I wonder if we have a problem where because like we're doing pointer arithmetic here, and if we're doing add, are we inferring that are we inferring that just because we're doing an add that temp.2 is an integer, and that's blowing our stuff up? Because they're actually pointers. Oh, this is not going well, fam. Okay, let's step back. I wonder, yeah, are we cooked, chat? Yeah, we're cooked. Maybe what we need, I suspect that's what's happening is we're looking at some stuff here and we're going, yep, that thing because we did add, which is not exactly what's going on, but that, oh yeah, that's an integer. That's kind of my suspicion, because why else would that, like, this variable temp.to, which is clearly a pointer, because we've just copied this pointer into temp1. Okay, so this is the beginning of the free space on the heap. We've moved that into temp1, so this is a pointer to a spot on the heap, right? And then we just move it directly into this other variable, and then we offset it by 16, and that's the allocator, right? Maybe we just have a bug in here, because this translates, where's our allocate? The other thing I was thinking is that we might do like a conditional insert for dictionary, where like insert it if it doesn't exist, if there's such a thing. Upsert. What was it, like something has in Erlang has insert new or elixir. Okay, well, don't really like this. Okay, so here's our allocate. So we're saying that type t here, whatever we're allocating, becomes that variable. So like in this case, this should be allocate 16, right? I don't, where's this move temp1 coming from? Are we doing that here? Our expose allocation should be injecting this logic, right? Okay, and this int is just our variable names. Right, so we do generate fresh variables. I think that these temp variables are coming from remove complex operands. Like, you know, nuvar temp dot something, right? All right, what function is this? So this is expression. So the only place it would, the atomic would generate this new variable would be if we have this allocate, yeah. And that would turn into a let binding, right? So what's not clear to me is why we're getting these spurious moves. So we look at what select instructions does. What? Okay, are we? Let's just look in this file for free pointer. It's only in this spot, right? So how are we getting a move a free pointer into temp.1 rather than R11? Remember, this is before we've transformed and assigned anything, so we still have variables there. All right, well, let's look in this file for allocate. Allocate. Okay. It's just right here. I don't see how we would ever generate this code. Did we accidentally drop something? Oh. Temp.1 is free pointer. Wait, what? Okay. I'm getting so confused. Like, how do we generate this garbage? Okay, so here's one where it moves free pointer into R11. Right, and then adds 16 to free pointer. Okay, so this one makes sense. Oh wait, so this is actually, this is not, okay, this is the if. Like, okay. So temp.1 is integer, right? That's fine. Okay, I was mistaken. Like, I was like, this is for the purpose of the comparison. Do we have enough space? I was freaking myself out there. Okay, so that's actually fine. Temp.2, yeah, that's an integer. Where we need to be sure that things get, so, right, the alloc2, so vecinit 5 and alloc2 and alloc6 should get spilled to the root stack, which is in R15. So what do we actually get? Let's comment that out and let's print that. Okay, this is fine. Let's see. So we're moving into R11, right? And then we bump. Okay, and then we move R11, right, into 0 of R15. That makes sense. So this is the first vector that we allocate. And we've got its init value, that 42 inside that vector is in RDX. So we're moving RDX into that slot. Interestingly, it's doing that. I guess that's okay. Like, R11 has not been changed yet. Okay, and then it's, so this is because this is read from RDX is reused. So this is the tag. Yeah, I think that's wrong. Because note we've already, like, these will get removed. Or they shouldn't get removed, but this is a spurious move. So this is the initialization of that field in the vector pointed tat by R11. The problem here is this is, okay, I'm reading this wrong. So it's just writing 0 to RDX. I have no idea where that comes from. And I forget it's like left argument goes into right spot. So this is actually, okay, now move the pointer into RDX. Okay, so this is going to be in the, this is like, hey, take that first thing off the root stack, and that is going to be initialization for the next round. And then we're going to see if there are 16 bytes to allocate and so forth, and jump to block 2 and block 3, yada yada. And then eventually we end up in block 1. So now we have root stack of 0 in RDX. Okay, so we're bumping the free pointer, right? By 16. We're moving the tag into the new slot in R11. So we've copied the free pointer and we're bumping it by 16 bytes. So R11 points at the 16 bytes that we need for this vector. Here's the tag, and this has to do with, it has one slot, right? That's the 3. And it has that 128 is, I'm sorry, not 130. So 2, bit 2 is the, there's one thing, and then 128 is, hey, that first thing in there is a pointer. Okay. So then it, but here's the problem. It's moving this into R0 of R15. So we have an orphaned object at this point. Technically, I mean, it's still a root, right? Even though it's fully contained in this other vector. This maybe comes to a more philosophical question. Is that actually a root or not? Or is it that we don't ever refer to it outside of that constructor, right? This constructor right here. And so it's not a root. The other thing is that we never refer to it outside of dereffing the whole thing. I almost feel like we need a more complicated example to see if the count of the root stack size is correct. Yeah, it's a very good language design question, and like there's not a ton of detail given in the book about this, because I think in this particular case, yeah, maybe it's fine because it's not actually a root. This is a root. This one is a root because this is not reachable from anything else. I wonder if you had something like, hey, you know, let A equals this, let B equals this, and then you put A into 2 different vectors, if it would get spilled onto the root stack. And it probably is the answer. Because you would have, you know, it wouldn't be completely contained. It would be like 2 things refer to that, right? That might be an interest. Let's make that program. Let's make that program, and then I maybe can answer my own question. Okay, so we're gonna say multiple roots. Okay, so I'm gonna do okay. Let's do like let A is vector 42. Okay. And then we're going to do let B is vector of A. And then we're going to do another let, which is, well, no, let's not do that. Let's do the thing is we're creating garbage here, right? Like that's the whole point. We're going to say vector ref vector of A of 0. And again, we have to unpack this again, right? This is going to be a complicated program, but what we're going to say... let's just do plus. And then we'll do vector ref B 0 0. So we should get 84, right? This is the answer to this program. Okay, so let's do... Right, we'll do this. And let's go ahead and print all this goop out as well. I have no idea what the assembly for this should look like, or what the intermediate variables created are going to be. Oh, it needs to be pub. Let's just run that test, and we're gonna comment out this so we don't get printouts from that. Because what I want to see is like, we should get a root stack of at least 2, probably 3, because vector A, or A here, is reachable from the root. So we should get 3, is what I would expect. Because they have to be live at the same time, right? Like A has to be live both in B, right? And over this construction. So let me make sure I didn't mess that up. That's wrong. Oh, and not, my syntax is all wrong here. I hate the way they do lets. Why do you need both of those? Like, I think closure actually just does the square brackets. Okay. So this is a longer program, obviously. Okay. So it's going to start very similarly, right? We put 42 into RDX, and then we're doing the do we have enough space calculation. Okay. Then we jump to block 8 and 9, and those jump to block 7, whether we need to do the thing or not. Okay. So block 7, we're allocating a vector, right? 16 bytes for A, right? And the tag is 2, because it's size 1, right? And that goes in R11. It goes in 0 of R15. What did it say our stack size was? Our root stack size. It's 2. Interesting. Okay. So, so we've got our and then we moved RDX, which was our initialization, into R11. So we've got, yeah, we've got a lot of moving around into the same place, but so okay, so we've got R15 offset 0 is our vector A. So it's this. Okay, and then we're going to, because A is going to be used in the next construction, we move it into RDX. Okay, so RDX is going to be the pointer to vector A, right? Okay, and then we're going to do the calculation again. Do we have enough space? Okay, and then we jump to block 5 and block 6, and this jumps to block 4. So in block 4, we're trying to initialize B, is what I would guess. Yeah, so note A.1 is live here. Okay, so we're copying that into R11. Allocate 16 bytes. Set the tag. Now we're overwriting slot 0. I think that's a mistake. Yeah, I think we've got a bug here. Okay. Let's see what happens later on, because I want to make sure that even if it overwrites, that somehow A gets into C. Well, this constructor, right? It should still be live here. It should still get into here. Okay. Right. Okay. So we copied the pointer to A into the slot for B. I'm not sure why we're moving 0 into RSI. That's fine. Useless move that gets handled in patch instructions. So now we're moving RDX into R8. Okay, so A is still live here. It's in RDX. So we've moved it into R8. Okay. And then we do the comparison dance again. Okay, so we're going to see, do we have enough space? Okay, so jump to block 2 and block 3. Assuming we get the space, or we had the space, we end up in block 1, right? Okay, so at this point, B is in 0 offset of R15. A is in R8, right? Because that was, where did that move go? Did I mess it up? All right. Okay. So here we moved A into R8. So up here we should see use of both 0 R15 and R8. Okay. Okay, so we're allocating. We know that it's basically the same type as B. Okay, so we move. Yeah, so we've got R11, this pointer that we've just allocated into 8 past R15. Right, so this is actually 2, right? And we do get 2. So this is for C, right? This is what we're allocating here. Okay, and then we're moving R8 into that slot inside our third vector. Okay, and then we're pulling it back out, back into RDX, and then we're moving into R11. That's interesting. Okay, let's trace the provenance here. So we've put A, which is in R8, into 8 past R11. Okay, I don't know what this move 0 into RSI is. That's fine. We'll figure that out later. Oh, this is what we're going to deref, right? Is it? Okay, I don't know what order of operations is going on here, but okay, so this is the vector R15 is the vector we just allocated right here, right? That's our C. Okay, so this is C. We put it in RDX. We put RDX in R11. That's just we want to deref off of R11. Okay, then it's going, hey, we have this vector inside. Let's move it into this root stack spot. Well, it's fine, I guess, because we're going to throw away this vector that we just allocated. Okay. And then we take that and put it in R11, and we extract. So this is getting slot 0 out of this vector we just created. So we just took this one, derefed into it, and put it on the same stack, root stack spot. And then we deref it again into RDX. Okay, and then we're taking B, which is in 0 of R15, and we're moving that into R11, and then we get the offset of that into, so we're derefing out again, and we're reusing the slot. That is so weird. It's not what I would expect, but it's not incorrect, right? It's just that this root is no longer live because it's gone after this. We don't use it again. Now, if we had further, like if this were a begin and we did some extra stuff, like maybe it would live. But the liveness analysis has said, hey, after you do this vector ref 0, B is dead. It's no longer live. You only care about what was inside that deref, and then you're going to deref it again. Okay. So we pulled out the inner vector into 0R15, and then it's like, hey, get this into RCX. So we have the inner value of this newly constructed one, the very inner value. So we have 42 into RDX and RCX. We move RDX into RAX, so, and then we add RCX to it. So we're basically just saying, hey, RAX is the return value, so this is the add instruction. Okay. I think I've convinced myself that this is okay. It's just not at all what I expected. Well, I didn't expect the root stack to get its slots reused. I guess that makes sense because of liveness analysis, we've determined that those things don't conflict with each other, right? But that is a little bizarre, and I'm not. I think it's okay, but I'm not convinced that it's right. Okay, so I think that I've convinced myself that this is okay. So what we can do, and I know it's sort of it's sort of like, hey, we know the answer, and we're not actually basing that on anything. But if you see, like, we did this same sort of operation in multiple places, where if the outer thing is no longer going to be used just because it's not live. This vector ref says, hey, I'm consuming that. You're not referring to it anywhere else. Then yeah, you don't get a big root stack. So that's really interesting. The other thing I didn't expect, and I suppose it has to do with yeah, I would expect R8 not to be used for it. It's just really interesting. Okay. It's funny that this works. This to me, it's really funny that this works. So I think that yeah, let's get rid of those warnings. There's a bunch of now we need to like consider can we make these other tests pass? And that may just mean we need to adjust what the assertions are, and make sure that we're not hand rolling this business. I think these are going to fail. Let me make sure that we resolve those warnings. Yeah, okay, so we're not printing out the program anymore. Yes, we got one failure. So the basic test, and I think it's just that we have new stuff and it's not being accounted for. And there's a question about, okay, so really what we care about in this is not that the programs are identical. We care about that the contents of this block gets assigned these particular assignments, right? And that we didn't use any callee registers, and there's no stack vars, right? So I think that what I want to do is, rather than this like this flat equality, we're going to say we're going to, yeah, let's comment out this and say let p2 is allocate registers of p, and then we want to say p2 dot stack vars should equal 0, right? P2 dot call used callee should equal set dot new, so an empty set. And then we want to do something like these are the set of instructions, right? So we'll say insters 2. Yeah, insters 2. And then we'll deal with that in a minute. So we've got the essence of what we need there. Well, we can say p2.types should equal p.types. So we're saying we're not transforming that at all. And then p2 root size should equal 0. Okay. So those are the basic things, and now we can go into, let's go p2 dot body, which is a dictionary. We'll do dictionary get start, and we'll say should be okay, because that'll extract the OK and panic if it's not. So we know we have a start block. And then we want to say, so this is, what do we have here? We'll say start block is this. And that's going to be a block. And then we'll say start block body should equal insters 2. Okay, that's really what we were testing there. So let's run that again and see if we get it passing. Okay, so that's we didn't really change the semantics of this test. We just accounted for new things, and we also made it probably a bit more resilient to changes that we make next time. Okay, what did I change in here? Did I comment anything out? No, I just, okay. So in some ways I feel like I might be missing something in this whole thing, and like there's a little bit of mystery going on when you have this sort of generic algorithm, and then and like it's built on some principles, right? I'm still not happy with this this case expression we have down here in extract assignments. But it's okay. I think we just have to trust that all of our vector type variables are tagged as such in the types. So okay, so this is going to be finally 6.7 finish off register allocation. Okay, so our next step is going to be, sorry, not that, this. So we basically got done with this. We got the number of spills to the root stack. Okay, so prelude and conclusion. And here, I've gone over my original allocated time, but I want to keep going because we're very close. Okay, so figure 616, we'll jump to that in a minute, shows the output of prelude and conclusion pass on the running example. So our vector ref of vector ref of vector of vector of 42, right? In the prelude of the main function, we allocate space on the root stack to make room for the spills of tuple type variables. So what does that mean? So we do so by incrementing the root stack pointer, taking care that the root stack grows up instead of down. Does that mean that okay, so I actually think that our this should be -8, right? I think that that's the case, because if the, why does it say it grows up? I would expect that it doesn't change then, but no, that makes sense. So like, let's say you need 2 slots. When you're bumping the root stack pointer, you're going to add 16 to it. So the root stack pointer grows up, but the 2 slots that you took are, well, it actually goes up by, it would only go up by 8, right? No, no, you'd still need to allocate 8. So like you would bump it by 8, and that's a new thing. But then you would go that one slot would be 0. So it's like exactly what it's pointing at. But if you bumped it by 16, then you would have 0 and -8, right? Because you moved it 2 words, and so now it's pointing at this word, and then you have 1 word before it that can be used. Okay. So let's make sure I didn't break any tests. I shouldn't have, but yeah. So I think we'll just commit that. Okay, so what we need to do is go into prelude and conclusion. Okay, so this is about frame alignment. Okay, so we need to have a new thing here, which is something like allocate root stack, right? Right, okay, so save registers is just set to list used callee. Okay, so we're gonna do let's go to generate main. Okay, so let's have a look at their example now. 6. Okay, well, yeah, that doesn't tell us anything. I thought it was going to show us some code. Okay, so here's main. Oh, yeah, it's the one above. The jump there is weird. Okay, so for our one spot, interesting, they're doing this call queue initialize. So okay, so this is they're handling the stack alignment and the caller save callee save variables, right? Or callee save registers. Then they're saying this is how big the two stacks or the two heaps should be, because these are the RDI is the first argument to initialize, RSI is the second argument. And if we go look at the supporting C code, which I have, I think, linked up here. Yeah, so if we look at runtime.c, or we could even look at runtime.h since it needs a header file. So these are the static pointers, right? The root stack begin, root stack end, so forth. And so this is the root stack size and the heap size. They're just saying have 64K of root stack and 64K of heap. Okay, so that's what this is. Call queue initialize, and then they're saying move this root stack begin pointer into R15. Okay, so in our code, so here it's all of the things we need to push. The alignment, and we need the root stacks, not the root stack size. We need input slots, we'll say. And here's the problem. We need to change this to x86 global. So now we can go input dot root. Really? Is that what we called it? Yeah, I know there's two arguments. I just want you to show me what that is. Root stack size. Okay. And here, this will also take the root stack size because you need to okay. And then so let's go to generate main, and this will take a root stack size. We'll call it slots. I don't know. It's going to be an int. Okay. So after the alignment, I need to make some adjustments here because this, so body is going to be that, and this will be x86.new block, right? And we'll need to do the same down there. That's okay. Okay, so we've got, we need to call this initialize. So let's just make some here. Pretty certain that that was like, yeah, you do the push and the alignment first, and then you call initialize. So we're going to say xa move q register psi. That goes into RSI. So x86 immediate 65536. And into, I'm sorry, into RDI and RSI. And then we'll do call Q initialize parity 2. Okay. And then we do move Q global root stack begin into register R15. So this is we've called initialize, so initialize has filled in those pointers with allocated space, and then we're going to say, hey, our root stack starts here. So we're going to do append initialize. So that'll get us. The interesting thing here is we maybe could say initialize could be empty if we don't ever need the stack or ever need the heap, right? Like if our root stack slots are 0, we don't need to do this because R15 will never be accessed. So if we say 0, then we can just return the empty list. If it's like slots, okay. And then we can also do, this zeroing out. Oh, interesting. I see. I see. So the stack is basically 2 pointers. There's the beginning, and then there's the current one. Yeah. Root stack end. Right. So this is like, maybe when we allocate on the root stack, we should check if it doesn't equal root stack end. Okay. So basically the collector starts from what you pass in, and will decrement down to root stack begin. So we need something like a range, 0 to whatever. Let's see what Gleam standard lib can give us. Either int or something. I know exactly what to do in actually, it's really just like we'll do a function. Not indent. We have some duplicate stuff here. Why didn't we delete those before? Yeah, we don't need this because we have the whole program to text then. I think the only thing we need to add is the global main to it, but sure, whatever. We don't need to use this string tree stuff because we've got the other bits. Okay, this is x86.new block. Splat that with body is those instructions, and we'll come back and fix that later. Okay, so if we have a number of slots that are greater than 0, then let's just make something that says 0 out root stack slots. Okay, so this will be like we'll have an accumulator, which is a list of x86 instructions, and we'll have a count, which is an int. And if count is 0, then we're doing typical recursive stuff here. We just return the accumulator. Otherwise, we do we need to add an instruction. So we'll do, I think this will come in the right order. What we want to do is call 0 out root stack slots with, we splat the accumulator, right, on the end. And we're going to add x86 move q. And this is, what did they do in here? So they move 0, right? Immediate of 0 into dref. If there's one slot, we subtract 1 from it. And so we'll say we want to do R15. And this will be count -1 times -8, right? And then we'll pass count -1 here. Okay. So now we can say we can append this to 0 out root stack slots of empty list and slots, right? So that'll give us all these instructions plus this initializer. And then the last thing we need to do is add 8 times the number of slots to R15. So actually we can put that here, right? So we can do, because this will be added in reverse order, right? We'll say 8 times slots to okay. Hopefully that is not too confusing. What do we got going on here? We need another print. There we go. It's like, why is it not reflowing? Okay, so we've got our 64K of our root stack and our main stack. We've got, and we call initialize, and then we move root stack begin into R15. And then we loop through the number of slots that we're going to use and initialize them to 0. This is like special indicator for the garbage collector that, hey, this doesn't point at anything. And then we bump the pointer up to the top of the things we've just initialized. So we did set this to 0. Oh, interesting. This is not negative down here. This needs to be not negative because we're initializing it before we move it. So we're zeroing out those slots before we move them. So we don't want to decrement. We could decrement before the root stack begin pointer. That would be bad. Okay, so that's the initialization, and now in the conclusion, we just have to have the root stack. What do we call it up here? I want to be consistent. Root stack slots. Int. And let's see here. So we would decrement first. So I can put that here. Actually, we can say let root stack pop. And if it's 0, then we just have an empty list. If it's anything else, then we'll do x86 sub q, x86 immediate, count times 8, and R15. Okay, and then we can go Okay. And I think that that will do it. That wasn't so bad. So what I want to see now, and before we call it for the day, actually I'm only half an hour over my normal time. Let's look at the test. It's going to be broken. Let's get rid of program to text and anywhere that we've referred to it. Yep. So I don't actually think that that's an important test. The main thing that we need to do potentially is update our program generator to like tag the main block with this .global main. It's not a big deal, but we can do it. Okay. So I think that the main thing here is we need to change this to x86 global as x86. And here we've got to do a new program. And this is body. Is that. This is what would that be? That'd be stack size, right? Stack vars. Okay. Okay. And that needs a function call param. Okay, so this is x86 new block. I just need to make sure that we update all the things. Okay. And we need to do the same treatment down here. And again, this is a straight equality thing. It might be okay in this case. Stack vars. You know, the other thing we could have done in this is gone with that like 2 different languages and remove the variables and the other things that we don't care about. So it's a simpler thing, but okay, we don't need set. Okay, so that still generates the same code for this particular program. But I think what I want to see is what it generates for main for our programs that actually use the stack. So we should be able to figure that out, right? So let's make, I don't know, generate allocations test. Okay. Let's do our typical thing. Like we did an allocate registers test, and we can just add things to it. We're going to do this. The other thing here is I'll need to go back. We need to look at patch instructions. I don't think that there's any changes to that pass other than updating the languages that it points to. So Right. So I think that what we need to do here is let's go ahead and do this, and this is going to be block. It's just updating the body of it, and I don't think that there's anything else here. All right, this is just making sure that when you have two derefs in an instruction, you have to move, like you can't do two operations on memory references. You have to put one in a register, and then do the move. Okay, I think that, let's look at the patch instructions test. Make sure that this is updated. Yeah, this needs to be changed to x86 global. I'm not going to let it autocomplete that for me. And we're going to have to fix a bunch of that, just like we did in the other tests, which is okay. And here we're going to say base program. And this is going to be body. And this is going to be base block, or base block. Body is that. And this is going to be stack size. No. Stack bars. 24. Is that right? Yeah, I guess so. Okay. Yep. And then body is this. Base block. Body is this. Stack vars 24. Okay, that like actually doesn't matter that much because it doesn't even look at that. Okay, and this is testing that you can't move to like a deref into a deref. You have to move it into REX first. Okay. At the top of this next test as well. I'm going to reuse it. Program. Body is that. Stack vars is 24. Y'all can't see it, but my cat is like on my lap and glued to me. Her chin is on my list, or on my wrist, and it is challenging. Challenging to get through this. Okay. Let's see here. So I'm gonna get these in here. Yeah, I think we can simplify this base program. Body is that, and we can get rid of these extra variables. Okay. Okay, here's a case where we can go start block is that, and we can say start block body it should equal that. Okay. Need this. Oops. Hey, it was still in my paste buffer. We will finish today. I am determined. I shall not be deterred. I might be the turd, but I shall not be deterred. Okay. And then we'll say this is start block, and again we'll say start block body. Okay. That should have updated that. Let's comment this out for a second. I want to make sure that patch instructions still works. What is our compilation error? Where it is? Where is it? It's right here. Oh, okay. So we need to do base block. Body's that. Okay, easy enough. Anything else in here? Nope. Okay, so patch instructions didn't need to change. Looks fine. Okay, so now we're going to, what we want to test here is that we get what matters is how many root stack slots do we need, and then what's the alignment like. So we could say let's make a program, and we can do the whole like yeah, actually that's probably useful. What was I going to say? We can copy this business, right? So we put not that business. Where are we? Copy that business. There we go. Okay. Import that. Okay. Import that. Import that. Import that. Okay. So this, we need to import, yeah, here. EOC langs ltup as L. Okay, go down here. So now we have this, and we need to put the other passes on here. So we've got build interference. We need to do allocate registers, and we need to do patch instructions. Okay. So do the same business we did before. We're going to take that example. Let's do both of these examples, but we'll start with this one. Okay, so we know that this one, what I want to do is I want to say p dot root stack size should equal 1. And this is just a sanity check. We've checked this elsewhere, but I want to make sure that that's there. The other thing is stack vars should equal 0 in our case. So those are the things that are we should also be used callee. It should be an empty set, and I'm going to have to import that. Okay. So now what we can say is let's pass our let's generate the prelude and conclusion. Okay, and then we're going to do let assert okay, and this will be the main block. Dict get from p2.body main. Okay. And then we'll say, let's write out what basically this, right? This is what we think the instruction should be. So we can do that. And we can even do that before we pull anything out. This is what we expect the main ones should be, and this is what we should expect the conclusion ones to be. We can do a little pattern match here. And let's do main body should equal, this is going to fail on our first pass, but we're going to write it out. Okay. And let's duplicate that for conclusion. And we'll say conclusion body should equal this. Okay. So let's write this out. So we know we're going to have push Q of RBP. And this is going to be a register of RBP. Okay, and then we're going to have, hello, Renard Saunders. Welcome to the stream. We are going to wrap up real soon, I hope. So we push RBP, and then we move Q, our register RSP, yeah, into x86 reg of RBP. Okay, and then we're going to subtract, since there's no variables here, it's going to subtract 0 from RSP. Right? Okay. Now is here where we initialize. So let's do move Q 65536, and that's going to move into RDI. Okay. And we'll do the same. Here, let's just copy that line into RSI, argument 2. And then we call Q initialize with 2 arguments. Okay, and then we're gonna move Q, the global variable root stack begin, into R15. Okay. And then we're going to initialize the slot at what R15 is pointing to. We're going to 0 it out. R15, 0. Okay. And then we're going to add. So we're bumping the R15 pointer, the root stack pointer, by 8. Okay. And then we'll jump to start. So there's our instructions for main. And then conclusion is going to be this. So let's go ahead and write that out. So we're moving R15 back down. Oops. Okay. Let's get multiple lines so I can have my sanity. Okay, and then we're going to add... So this is just reversing what we did up here at the top, the sub Q, even though it doesn't, we have no stack variables used here, so it'll be 0. And then we pop RBP off, and then we ret. Okay, so that should be our test. Did we do it right? Okay, so we got a problem. It's not telling us which line, but I'm guessing by this, it's the prelude, so the main. What do we have different? Okay, so we push RBP, we move RSP into RBP. That's standard. Okay, so it's actually sub Q8. Why? Do we have a bug there? Let's look. So what are we doing here in... Oh, it's about alignment, right? Well, 0, let's see. So compute frame alignment. Oh, we add 1 because we always save RBP. That's interesting. Okay. Okay, so actually either here in the book it's wrong, or it's wrong in our code. Regardless, I'm okay with, because this was like supposedly correct previously, I'm okay with adjusting the expectation of our test that this is actually going to be 8 here. It's interesting that it has to be aligned 16 bytes, not 8 bytes for the stack pointer. Okay. Okay, so now it passes, and we can get rid of some of those unused things in here. All right. So the last bit, I think, is we should, in our format block, let's say let prefix block name. If block name is main, then what we want to do is we'll say doc concat. If it's anything else, we're just gonna prefix an empty document. Okay, so what we're doing here is we're updating the actually we don't need, yeah, we need the line. I'm gonna put a tab and say global, global main. I think that's supposed to be a tab, like 8 spaces, it looks like. Again, this is just so that we can make sure that we have that in front of our main function or our main block when we output this. This is a signature, a signal to the runtime that this is the entry point for this module. So and the linker. Honestly, that's for the linker. It's saying that this is a global symbol that you can link to. The rest of the symbols are not symbols defined in that file. Okay. So I think we've got it. What we should do for fun, at the risk of running even longer, is let's update this, because basically anything beyond select instructions we should be able to output, right? Which means that we could hook that up to our UI and play with it, which is half of the fun of this. So why don't I make a commit real quick, and we'll say this is chapter 6.8, prelude and conclusion. Okay, and then we can go in here and say, like, here, we can put additional passes in here. So after select instructions comes build interference. Doesn't do anything. Uncover live would, I guess. Right? Build interference is like an internal one. But uncover live affects how we output the program. So let's do, this is uncover live, and we will have a build interference skip, allocate registers, patch instructions, and prelude and conclusion. We'll say generate so that we're consistent with our naming. So this is, yeah, let's just copy these in here, put commas after them, and then we need to get add the missing patterns. So allocate registers, and I may reorder these clauses because it tends to put them in alphabetical order, which is fine, not the order you declared them. Patch instructions and uncover live. Okay, so we'll move that up and then that down, and now we're in order. Okay. And we need to do the inverse here, so just copy that in here and flip the arrows. And we need to update the default last pass is going to be generate prelude and conclusion. Okay, so these are just like signals to our UI of what to be able to do. And then down here in compile, we need to add the additional patterns here. So let's see, uncover live will come first and that will come last. So this is really just about like copy paste some stuff and update. So here we're also going to pass it through uncover live, and I need to put the to do back in there so that, yeah. Okay. And then we'll do another copy pasta. This is like, you know, there's probably more elegant way to do this, but this is good enough for me. And here we'll do patch instructions. And once more with feeling. Okay, so now we've added those. Hey, that's all we had to do to add those to our UI, right? So let's do Luster dev build. Okay, and then we'll say start. I don't think you technically need to do build and start. I guess start also build it. And let's open that up. And okay, so now you note here in our drop down, prelude and conclusion is last. So let's throw in here our typical program and play with that. I love that that was really quick to update. Oh, what's going on here? Oh, that needs set. Okay. Let's get our program, our favorite program. Here we go. So I don't have to type it. Okay, so if we start with parse, and it's fine. Type check, we got type wrappers on things, that's pretty cool. Shrink gets rid of and or, turns them into if. Uniquify, we have no variables in this program, so Uniquify doesn't do anything. Explicate control, so we've jumped through some passes. Now we're kind of in, this is the C-like language, right? Pretty cool. Okay, select instructions. Now we're starting to see it looks like x86 assembly with variables. And the live before sets are printed there, right? So that's, select instructions happens before we do liveness analysis. We do liveness analysis, we get those printed out. Pretty sweet. Allocate registers. So now we should have no longer any variables. The live before sets are unmodified, so wait, did we do that? I think I have a bug in here. Might not have added that in the right place. No. I need to look at the console. Did we mess something up? Okay, pattern match failed, no pattern matched the value at translate location. That's too small for me. Old eyes. Okay. Okay, allocate registers, line 129. Line 129. It's interesting we didn't see this in the test. Okay. So, how did we get something that wasn't assigned? So pattern match failed. No pattern matched the value. So there was this is interesting. Let's go back here. What would cause that? So the interesting thing is we actually tested this exact program on every pass, did we not? So the question is, what did it, like what location was it trying to translate? Here, translate location. So this error should have the value on it. Can I? That's just the stack. Do that, because I think that this is I want to see if I can get some more information. Okay, so right, this is the error we got. The inner part. Value, no, 0. So this is a let, like where we originally saw it was this let assert. Right, and so value is $. What have we got on value? It's just error 2. I thought we were looking at oh, well, yeah, okay, so that's just error. The thing here's what we could do is we could put a breakpoint here. That's probably the better way, and then we can see what variable was not. Here. It's fine. We'll just leave that in there. Okay, so we're looking for _8. That's interesting. So we had something. Assignments is empty? Are we doing this before we... Did we introduce a bug somehow? Or is it that our graph doesn't work right? I wonder if it's just that. If it's just our... We never got this far on the front end, and... Right, so input is x86 program. Do we have that over here in our local variables? Yeah. So okay, so you got like, this is how the dictionary is implemented. It's like a hash map. Okay, and the list is, you know, there. So what's interesting to me, so you've got the graph. I wonder if we need to use a different kind of graph. Okay, so there should be no used callees. We've got, you know, so we have types for _8. It's just, it's not, the code is not running correctly on JavaScript, and I'm wondering if it's just a problem with our, here, you can run. Yeah, I think that that's something to resolve for another time. I may do it off stream. I've gone way over. I appreciate that you all stuck around. I feel pretty confident about our output, but we need to resolve some issues with JavaScript. Next time we will start on game programming in Gleam, which should be really fun. I hope you'll join me next week. Thank you.